Okay, so let's get the screen shared here. Looks good. All right. So today we have a lot of ground to cover, and my question to each of you today to kick off the class session is, has anybody ever sat down with you guys or had a chance to take yet where there's a whole range of menu tool set statistically to walk through the whole set with you to say you could do this, you could do that. You should use this analysis for this tool to answer this kind of question. Definitely don't use this kind of sort of data, but use this one instead. Anybody ever sort of help sort out the huge array of statistical things? Certainly, yeah, a little bit. That's on yet. Okay, so in that case, let's run through this. And the intent here isn't to essentially duplicate the effort of your stats classes at the graduate level, which are going to teach you how to do things like the specifics and the computations of hypothesis testing statistical procedures, or flow modeling, structure equation modeling, stuff like that, how to actually do the mechanics of them. Here we're just trying to get sort of the first researcher's sense, or a more complete researcher's sense, if you've heard any of this before, on what's the higher level, what's the more sort of conceptual or step-by-step approach that you will probably be taking some branching path in when it comes time to analyze your data, maybe this autumn after you've collected it this summer. So let's do that today. First thing we always do with our quantitative data, and this is strictly a quantitative and statistical or a numeric analysis discussion for today. We'll talk about qualitative or text or speech-based analysis on another day. We all pretty much end up doing the first several steps in this workflow, no matter what the data are, no matter what the project is, no matter what your timeline is, because we just got to know some basic fundamental things about every single one of the variables of data that you are collecting. We want to know what are all the sort of the univariate summary statistics of each one of the variables, each one of the columns in your data set. If your rows are each of your observations or each of the individuals or the samples that you took, the columns in that spreadsheet or in SPSS or SAS or whatever software you're using to analyze your data, each one of those captures a different attribute or characteristic or truth about, or observation about the phenomenon that you're studying, right? And so we want to know what's the range in that data, what's the maximum value, what's the minimum value in that data set just for that one column. We'll talk about analyzing things across columns, multivariate analysis, a little bit later in class today. But what's the average, or what's the median value if the data are better described by an average or a median? They're both measures of central tendency. What single number do all of the numbers in that column, or all of the numbers in that variable, where do they cluster around? That's typically described as a mean or a median, or less commonly a mode, the most common value in the data set, which may or may not be close to the middle value of the data set, that is named the median in English. But for different data sets, or different variables, the correct or the wisest answer might be median for that one column. And then for another column, maybe right next door on that same spreadsheet, the correct or wiser answer might be, I need to use the mean or average to describe the middle of this data set, the center, its central tendency, as we tend to call that in statistics. Okay, so your stats classes, again, will take you through, and we all probably at this level already know how to compute the average value of a set of numbers. That's fine. But as a researcher, we always want to get in the habit of automatically, as soon as we get some data, We go through a bunch of error processing and checking, looking for any missing rows or missing cells, looking for any typographic errors, if anybody has been hand typing in or writing down data physically instead of getting data automatically typed up for you essentially by the digital sensor, like an electronic balance or a LiDAR system. You're not typing in the coordinates of each of the points in a point cloud of a LiDAR data set. That's already done for you by the computer. But you do want to check for any impossible values, right? If part of your data set is the mass of each of the trees in your plot across the Shawnee National Forest, and you have a field procedure for estimating the mass of each tree, let's say, mass cannot be negative. So if we have a negative value in the mass column of our data spreadsheet, well, we want to know that, we want to identify it, and essentially do just basic cleanup of that data. So as the researcher, when you find an impossible value or a value that was clearly mistyped, it was a typographic error, it's not the real answer, you as the researcher need to figure out what to do with that in this error checking and preparation phase. And this is all right before we get into the basic univariate descriptive statistics characterizing and summarizing each of your variables. Okay. So, for example, in one of my PhD students' data sets, we were just doing this yesterday, actually, and at the end of last week, we asked people in a survey a quantitative question, a question that is answered by a number in the survey, and one person had answered the question, what year were you born, as 9174. So when we ran the univariate summary statistics, including what is the maximum value in this one column that is capturing all the data for this one variable out of the survey, one question in the survey counts as one variable initially. And somebody had typed in on their cell phone, I was born in the year 9174. Now, obviously, this can't be a real answer. What do you think happened with somebody typing in their birth year and they typed in on accident, it's 9174. What happened? Say again? Okay. Outlier. Yeah. So when we plot these graphically, which is one of our later steps in univariate summary statistics, and at the univariate summary statistics level, sometimes we clean the data up as much as we can, and then we run the univariate statistics, mean, median, mode, and we get the range of the data and so forth. And the range is this impossibly huge number. Then we go back to the cleaning step and go, okay, we found this one value that's really weird. Let's go back to our original data. Clearly, our initial cleaning didn't spot this one, but now we're starting to do our univariate analyses. We found this data. What do we think happened? Exactly. They just switched the digits, right? So this is a less common one because 1 and 9 are not next to each other on an English keyboard. They're at opposite ends of the keyboard, but this still happens. If somebody's typing very fast, sometimes their right thumb is a little bit faster than their left thumb, and they make what's called a transposition error. This is a subspecies of typographic errors. One way to commit a typographic error is to have a transposition error, where I typed this digit before I meant to type this digit. I meant to type both of those digits, so it's not just a general typographic error where instead of typing numbers, maybe they type in Q974. Well, the Q key on an English keyboard is very close to the 1 key, and so you just hit the wrong one with the correct finger, and we would catch that error because Q974 is not strictly a number, right? And your stats analysis software will say, wait a minute, what do you want me to do with this value? It's not even a number. I can't count Q974. So it helps you catch some of this stuff. But where it is a number, the stats software isn't smart enough to understand this is an error. So you, as the person, the researcher, this is where you treat your data set like the old Soviet Socialist Republic, where we trust what it says, but we also verify what it says, because there are errors in every data set. Or at least, even in a perfectly captured data set, there are still going to be statistical outliers among the data. And it is also your decision as the researcher what to do with those outliers when you find them. Some kinds of research projects, like we talked about earlier in the semester, have outlier values that are real and that you need to pay a lot of attention to because they are real. Other outliers are the result of a simple human or mechanical or electromechanical error and need to be corrected. So we just go into that cell and we delete the 9174 and we type 1974. And that is a sensible birth year. And in the case of my PhD students' work, once we corrected that, all of the other answers to other survey questions agreed with this person's approximate age. So in that way, we can't be sure that they weren't a time traveler and really are from the year 9174. But we can probably make an educated guess and say, all right, either I'm going to throw out this one value because it's wrong and I can't figure out what the true value should be, or I'm going to throw out this entire answer set, that entire set of answers by that person in that case, or that entire tree. Maybe we can't trust any other answers if we can't trust one of them. And that is true in some cases. Or we decide to make our best guess as the researcher as to what the person was trying to tell us and go with that. So when we have outlier values, we either keep them in because they are a legitimate answer to our research question or part of the answer to the research question, or we filter out just that one value, that one cell in the spreadsheet, or we throw out the entire case, the entire organism's worth of data, for example, the entire research site worth of data if each site is a row in the spreadsheet. Okay? Now, there's no single way to always choose among those three options. So you as the researcher want to talk with your advisor and say, how do I want to handle statistical outliers in our data? Now, your graduate level statistics classes will teach you how to compute z-values, which are another univariate statistic. Z-values are an additional computed statistic for each cell in that column. And considering all of those z-values together, you might have very small z-values, which means that they're all very close to the average value. Together is low. And sometimes you get a very large z-value, but that is true, or but that is in error. So you decide what to do with that. There is no single hard and fast rule on how far from your central tendency value, your mean, or the middle 50% of cases. So let's say we ask people their birth year, and the oldest answer we got was 1920. And if people are answering, this particular survey was about the eclipse last year in 2024. And the youngest person answered, I was born in 2015. We had a couple of cases like this, where the person, the respondent on the survey, was only 9 years old. The person answering 2015 is a correct answer. But for those cases where anybody is less than 18 years old, we're not allowed to collect any data on them. In the United States and in lots of other countries, there are very specific and powerful protections and boundaries around asking questions of human research participants when they are children, meaning they cannot give legal consent to participate in the survey. So when we find a value in the data, that means their age is less than 18 based on computing current year minus their birth year, then we know that we have to throw out that entire row of data. Even if they had really cool and interesting answers, we have to basically pretend in human research like that response doesn't exist at all, unless we have a specific and additional and much harder to get set of permission to have children's answers in the data. Okay, so the specifics of having kids in research, not really part of our class today, but we are interested in the oldest person that answered this is over 100 years old, and we could have one or a few people like that. Most of the people answering our survey were 30, 40, 50 years old, right? So if our average birth year was 1974, then our average respondent was about 50 years old when we collected the survey data in 2024. And then a very common additional univariate summary statistic is to ask, okay, so if I start at the average value or the median value, if it's not sort of cleanly, evenly distributed, what's the middle 50% of my data? What's the half of my data or my cases or my rows that are within 50% of the range, or 50th percentile or 75th percentile to 25th percentile, right? The middle half of all of our respondents. How many people are in that space and how many people are outside of it? So we have one person who answered, I was born in the year 1920. And we have, so 64, 1984. We'll say the range 1964 to 1984. People who are 40 to 60 years old are about the middle half of our people, our respondents. One person said they were born in 1920 and that they're 104 years old. Pretty cool. Over 4,000 people fell within our middle range, and our middle half of data set in terms of age, not in terms of number of respondents, but in terms of age. Okay. So when you compute the z-score, that is how many standard deviations away from our middle or average value, our oldest person in the data set was over 8 standard deviations, 8 z-scores away from the middle value. Now, a typical test, if you know nothing about the data set, nothing about the research study, a typical threshold or cutoff for calling something an outlier is going to be anywhere from a z-score of 3 away, so 3 below the average, or 3 z-scores plus the average. This one was over 8 z-scores away. So that means this is definitely a statistical outlier. One person out of 4,500 people said that they're over 100 years old. So it's our decision as researchers to call that a real value and say we're throwing out that one answer, we're throwing out that whole case, or we are keeping that one entire case and that one answer in our data set for subsequent analyses, all the bivariate analyses and the multivariate analyses and so forth. Okay, so the univariate summary statistics, this is going to sound crazy, but the univariate summary statistics are what help you to sort of just get to know your data, to explore your data. What is the maximum for this particular variable? What's its minimum value? Is it normally and symmetrically distributed around the middle value? So if we count the number of cases everywhere, like at the middle value? Do we get some sort of normal or Gaussian distribution? Do we get some other distribution like exponential, where the graph looks like it's super lopsided, it's completely loaded at one end and very low at the other end? So a lot of people were at the average value, only one person was at the extreme old value, and a few people were at the extreme low end value, right? It's interesting to do this part of analyses because this is you getting to know your data. This is the step where you find something you didn't expect. In our sort of more sophisticated statistical analyses, where we're a little bit further away from the directly observed characteristics of individuals in our data set, we tend to get less of exciting or fewer exciting surprises further we get down sophisticated statistical techniques. So this is the step to enjoy if you're a total nerd like me. And if you're just trying to figure it out, if you're just trying to get through your master's degree, you want to spend some good quality time with your data when you are well caffeinated or well rested, you're alert, you're feeling healthy and good. You want to spend good quality time on your univariate summary statistics, because if the time you're spending on your univariate summary statistics is not high quality, then any mistakes that you don't catch when you're looking at each of these individual values, they're going to confuse and make wrong or even invalid any test that you do beyond your univariate summary statistics. This is your chance to catch it and make your data set as perfect as possible. Okay? So, all that to say, have an interesting and thought-provoking conversation with your advisor as you are compiling your data set on how do we want to deal with our outliers? Do we want to throw out just the individual cell if it doesn't make sense and we can't make sense of it? Do we want to try to fix it? Do we want to just throw it out? Do we want to throw out that whole case if any part of that case, any individual value from that observation, that row in your data, if any part of it stinks, do we throw the whole thing out, be very cautious about it? Or is there something about the real outliers that we figure out are not typographic errors? Is there something real about those outliers? So for example, in the study of disease, epidemiology, the study of the spread and proliferation of disease, right? So epidemiologists studied and classified the COVID-19, the SARS-CoV-2 spread as a global pandemic, right? It's that field of study, public health. The outliers in a data set for how much viral load does a single patient produce, the outliers prove to be very important in understanding how SARS-CoV-2 spreads. We've got most of us that every time we cough out a few million viral particles onto anybody who's within 6 feet for 15 minutes or more. It's enough of a viral load to possibly transmit it to the next person with some degree of reliability, some percentage success in contagion, if you want to think of it that way. But there are a very few people in every population group, every city, every town across the world that turned out to be so-called COVID super spreaders. Anybody know what a super spreader is? Oh, this is so cool. All right, so we had basically a normal distribution, right? So everybody produces with each cough when they are COVID positive, a certain sort of typical or average or median number of COVID particles that sort of blast out, up to about 15 feet away when you cough, for example. Okay, that's some tens of kilometers per hour, and then the viral particles slow down because they're very small and lightweight, right? Like a very fine powder, you cough out, and then the particles eventually settle out onto a surface and die off. But every once in a while, very rarely, when they were testing people's cough to see how many viral particles individuals put out, they'd find somebody who put out, instead of, let's say, just to make up a number, 15 million on average viral particles, they put out 150 million or 1,500,000,000. So 10 or 100 or 1,000 times as many viral particles as everybody else tended to. And so epidemiologists had to look at, okay, so we know how likely a typical person is to cause COVID to spread to one or more additional people. That summary statistic, that univariate summary statistic, is called R naught, or R subscript 0. What is the contagion multiplier? So each person that gets sick tends to, on average, make 1.2 other people sick. The super spreader might, on average, just looking at super spreaders, outliers, people who are many z-scores away from the average amount of viral particles put out there, well, they can make 10, 50, 100 other people sick each. So, for example, there was a super spreader case identified in China. I believe this is the study back in 2021, probably, that identified the idea or the phenomenon of super spreaders, or helped characterize it and put some evidence behind it. Every time this individual in China went to the bathroom and flushed feces down the toilet, multiple additional people in his apartment building, which all shared a common toilet pipe, and the plumbing did not have a gooseneck in the bottom of each toilet to stop sewer gases from coming out other toilets, would make multiple other people sick in the building. Just happen to have toilets on the same sewer pipes that his toilet was on, right? So if you're a public health official, somebody trying to stop the deadly advance and spread of COVID-19, we learned to not only identify where the virus was present and who it was incubating and multiplying it, but we learned to identify through direct biological sampling, so capturing people's respiration, and also sampling sewage plumes from even individual buildings and so forth. We learned to identify where there are super spreaders and to quarantine that person especially, not to treat them any differently than anybody else, right? It's not that person's fault that they're a super spreader, but to keep lots and lots and lots of people safe, we can help do that much more effectively by figuring out how to quarantine anybody who is sick, but especially learning to identify super spreaders and helping to protect a lot more people, keep a lot more people alive in that way. Okay. So outliers are really exciting. Whenever you see an outlier, I want you to think of the idea that science often makes its big leaps forward instead of the much more common incremental tiny steps forward. The progress that you're making with your thesis is probably going forward. But every once in a while, we get a big jump forward because somebody spent the quality time during the univariate summary statistics running the average of every single one of your variables. You might have dozens or hundreds of variables to analyze. That's fine, whatever. You'll get through it. Looking for the average value, looking for the standard deviation, how much those values crystallize around that average, or are they way spread out from it? So is the average a good guess? Low standard deviation. Is the average a bad guess of what each individual value might be with low standard deviation? And when you look at your data and you think, oh, well, that's weird, because I expected 99 out of the 100 cases that I found. But this one case, it's not an error, it's an outlier, but it's weird in an unexpected way. That outlier means something. Those are the studies, those are the moments when the study goes from this is an incremental advance in human knowledge to this is a bigger leap. Because smart people that wouldn't be here, more highly intelligent, successful, and motivated folks to get to this point even. And so we're going to make pretty safe, sure bets on what we think we are going to find with our science and research. But we don't know exactly what we're going to find. That's why we call it research and not technology. So look for the outliers. Get excited when you find outliers. It might just be a typo. It might just be, well, your study just got much more interesting, okay? Because in your random sample of whatever population you're studying, you just found an outlier that breaks the rules in a way that's exciting, interesting. Okay, cool. All right, so univariate summary statistics, it's a long list of stuff. Most of you guys are probably familiar with most of these. So measures of central tendency, mean, median, mode, trimean, harmonic mean, geomean or geocentroid. Those are all measures of what's kind of the middle of this data set, whatever that data set is, lat long, coordinates, or viral load, or age, or mass, or cubic feet per second, or cubic miles of water in a large subterranean aquifer. Whatever the number is, what's the middle? What's the best guess? If you don't know anything else about the data set and you have to guess what the next aquifer over, like the one that you studied, how much is going to be there, you would guess the average, or the trimean, or the harmonic mean, whatever. All right. And then you also want to know how tightly or not do the actual individual values cluster around that. So if your range, that is the maximum value for that variable minus the minimum value, if those numbers are very far from that middle value, there's a big range, there's a lot of variability or deviation from that middle for any individual data point, potentially, okay? Or you might have a distribution where the range is large, but the standard deviation is very small. And so a normal or Gaussian distribution is shaped about like this. Not to scale, I'm not an artist. But a range that is large, but a low standard deviation, a low variance around that middle value, would look like this on a frequency chart. Okay? So when you plot the count of each individual value, how many times somebody answered or that you observed the middle value versus the maximum value or the minimum value or any value in between, this chart is called a histogram. A histogram is a frequency count of how many times you observed each value, and then those counts are turned into a bar chart and they're plotted in order from minimum to maximum or vice versa. Okay, so frequency chart might look like a bar chart, or excuse me, a column chart that looks like this. Sometimes, if the data set is absolutely enormous, like thousands or tens or more, tens of thousands or more values, we'll get a smoother looking plot, okay? And that frequency chart, that histogram, that frequency count of each value in the range of that variable, that tells you a whole lot of stuff. It tells you a lot of stuff. If it is a normally shaped distribution, this bell curve, this Gaussian distribution, as it's called, named after Carl Friedrich Gauss, pretty smart guy, who has lots and lots of things named after him in multiple fields of science. So pretty smart guy. We can run a lot of statistical tests that are designed to be run on data that have this normal Gaussian bell curve frequency chart. If your data are not normally distributed, like the lowest value or the highest value is also the most common one, that's an exponential distribution. Sorry, exponential distribution, right? if your statistical test is trusting you, because a statistical test is nothing more than a series of equations, it's not doing any thinking, it's not doing any reasoning, that's your job. If your data for a particular column, a particular variable, are not normally distributed, then that's a signal that you need to use a different kind of statistical test to answer the same sort of research question versus if that same variable was normally distributed. So, univariate analyses, figuring out the univariate summary statistics, range, mode, median, central tendency, standard deviation, variance, stuff like that. That sets you up for graphically inspecting the stuff. And you always graphically inspect. You put onto a plot the univariate frequency chart and you look at it, because your stat software will not tell you that you're looking at an exponential distribution or normal distribution, or here's a weird one. And this happens often. This is a bimodal distribution. There are very few values around the middle or median, right? But it's telling you that there's a median value. And if you try to run a regular ANOVA on bimodal data, where there's a lot of cases below the average and a lot of cases above the average or median, but there's very few at that central tendency value, that ANOVA test is going to give you a result, but it's bullshit. It doesn't mean anything because we didn't catch the fact that we're not satisfying the assumptions, the needs, the requirements of the ANOVA test, one of which is I'm assuming that you are feeding me, I'm the ANOVA test. I'm assuming that you're feeding me at least one input or independent variable that is at least possibly or normal-ish distributed. And the output variable is probably, most likely, normal-ish distributed as well. But if it's something else, that can break those equations because they are relying on trusting you to feed it real data that it can handle instead of real data that it cannot handle. Okay? So your stats classes will take you into the specifics of how to compute standard and non-standard, normal and non-normal distributions, and then give you tests, statistical tests, to say how normal-ish, how Gaussian is this distribution, right? So these are both approximately the same shape in terms of their range, their central value, but not the fatness of the peak, all right? The fatness of the peak is a summary statistic of the distribution that's called kurtosis. So your stat software is going to spit out a number for kurtosis. And if the number is very close to its sort of target value, then you have something, a distribution for that variable that is very close to the normal distribution in terms of its fatness or thinness. This is too thin to be a normal distribution. You could instead have a distribution that is too fat, too wide to be considered totally normal, right? So you're computing the basic first wave univariate summary statistics, average, range, standard deviation, stuff like that. Then you're plotting what those actual values are on the range that those values could be. And then you're computing second wave univariate summary statistics like skewness, which is a left skewed graph or left skewed frequency chart would look like this. It's sort of normal shaped, but a bunch of the data are to the left of the average value, not the median value. A right-skewed normal distribution or normal-ish distribution would look like that. Does that make sense? So first and second wave univariate summary statistics, and these are critical in telling you what kinds of tests you can run, what kinds of statistical modeling you can do, bivariate, multivariate kind of stuff. And you have no idea, typically as the researcher with any large data set, you have no idea what these results are going to be when you're out collecting data. So this is the interesting part, or this is one of the more fun parts of statistical analysis, exploring your data, as it's called, preparing your data, it's sometimes called, processing and prepping your data for real or heavier, more involved statistical analyses. It's all the same thing. It's just getting to know your data, right? What are the parameters of each one of your variables? All right. So that's univariate stuff. Once we get into bivariate stuff, then we're talking about one variable in relationship to another variable. So one of our big key ideas here is going to be something we mentioned in the other graduate class I'm teaching this semester called Anscombe's quartet. So let's make this as big as we can on the screen. This is 4xy scatter plots. So variable x is one variable, maybe age, and then the y column, or the y-axis, excuse me, is a second different variable out of that same data set. And the dots represent each case's x value and each case's y value. Pretty straightforward. We've probably all made scatter plots in the past. Raise your hand if you have seen anything like this before, have made something like this before. All right, most of the class, yeah, very cool. So Anscombe's quartet is one of the first things we want to do with every meaningful. I'll do this with every pair of variable 1 and variable 2, because it doesn't make sense to pair some variables together. Like, there's not really much of a reason to correlate anybody's day of the week that they were born with their weight. Since have no relationship to each other. And we know that, we're pretty sure that we know that previous research. So if you have the day of the week that somebody was born, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday, we don't bother plotting the answer, plotting the two-dimensional scatter plot for that pair of variables because it just doesn't get us anywhere, right? You as graduate students may at some point face the temptation to have SPSS or SAS or R pair every possible pair of variables together and plot them out and start running statistical tests like linear regressions. Blue line on each of these is a mathematical line equation that tries to summarize and predict these points. For any point that we don't know both values of, we can use this line to make an educated guess. Okay? That's called a simple linear regression. X essentially predicting or explaining, we know X or Y, and we know the equation of the line, then we can guess the other missing value. That's called regression. What these four scatter plots are showing are four very different data sets. Amen? You all agree with that? The first data set on the top left has a noisy, the line doesn't perfectly predict what each point will be on this scatter plot, but it's generally showing that when you plot this point cloud, there's generally a direction to it, and it's not totally horizontal. When you have a horizontal cloud of points or a horizontal line that summarizes or predicts those points, that means there's not a strong predictive or correlative relationship or correlation between this pair of variables, right? But in all four of these graphs, we do have a non-flat, non-horizontal line. So there is some kind All right. And this one, it's a cloud of points basically agreeing with this line. Now, the second plot, totally different data set, but it has the exact same regression line, linear regression line. But it's clearly a nonlinear relationship. We would call this a parabolic, right? So y value equal to some version of x squared, or 1 over x squared, or a parabolic, or a hyperbolic. The relationship predicting the value of y is some term of x to the third, or x to the fourth, or x to the fifth. And then the whole sort of equation of a curve instead of a line. But here's the thing. And so these other two graphs or scatter plots on the lower end, they also have the same, this is the correct regression line for all four. But here's the thing. Anscombe's quartet is 4 different data sets, and all 4 data sets have exactly the same, or very, very close to the same. They have the same average, same middle value. But this data set, this fourth in the bottom right corner, all the values are the same. All the x values are the same, and there's one outlier. And so maybe we look at the data and we decide, now this is a real point. We can't throw it out. It's not a mistake. It's not random error or happenstance. All these have the same average x value. And they have the same average for the y value of each of those points. And they have the same variance on the y variable. And they all have the same variance on the x variable. Variance is a fancy version of standard deviation for those of you guys who haven't had a chance to take your first grad stats class yet. Okay. The linear regression line, as we've said, is the exact same. It is identical for all 4 data sets. And the coefficient, the predictive power, the ability for that line to be a correct guess, called r squared, is also the same for each of these 4 data sets. And these are 4 very different data sets. They're completely different from each other. These are a trap. Because SAS or SPSS or R, it's going to tell you what the number is for average, median, or variance, or when you get into bivariate analyses, the regression line, or the coefficient of determination, r squared, which is a statistic of that regression line. How well that line predicts x or y values given the other value. So all this to say, this is your chance to plot everything. Have the statistics software for every single one of your numeric variables or quantitative variables. Plot out the histogram, the frequency count of each of the values, and look at it. Is there a spike way out at the edge that might be a bunch of standard deviations or z-scores away from the central value? And when you are grinding through your bivariate analyses, does x predict y, as in these plots here? Well, x predicts y equally well in all 4 of these plots, but the relationship underlying that prediction, the real world phenomenon that you're trying to make a model of or guess at out of your data, completely different across these 4. Okay. So this is the getting to know you phase. It's coming up in the summer. Fall, you guys are done with your right. So this is right where you do this first, and you do this every time for every variable. All right, let's cap it off right there. Let's come back on Thursday, and we'll start to get into what do we do with all of our data after it's beautiful and perfect, and we've checked it for gotchas like Anscombe's quartet or frequency distribution, multimodal instead of normal. All right. You know, there's some questions if you have them. Wise, see that. Okay. Cool. So, no matter what your study is, definitely do all this various stuff. Your study may then take you into any of the stuff that we're going to talk about on Thursday or not. You're not automatically on the hook for all of the rest of what we're going to talk about. Thank goodness, because it's a lot. See you next time. Thank you, guys. Go. Awesome. Awesome. We have it. Yeah, it's doesn't get used enough, I don't think. Yeah, mine's gonna dry it out too. So anyway. How you doing, Sherry?
I'm surviving.
Making it?
Yeah,
Okay.
finding things out that my parents never had written down.
Okay.
You know, my mom died.
Yeah.
We buried my mom and dad together,
Okay.
so we kind of had a double funeral.
So you go like going through the old family documents and stuff like that? Yeah.
I found out my mom was a classic depressionist for the Depression.
Okay.
Yesterday, I went through a box, found $3,000.